brought your laptop here, feel free to grab that already, because this is actually a hands-on session, an overview in agent-based modeling. I'm sure Python is a known a language for you guys, and we're very glad to have Thomas here. He's going to take us in this tutorial. There is also an online colleague. We're really going to be as interactive as possible. But for now, we want to welcome to the stage from Mesa, Thomas Pike. Please give him a warm welcome.
Thank you. All right, so good morning. Hopefully, my colleague Jackie Kazel is online to answer chat questions, since this is a tutorial. So if you got a laptop, you can feel free to bring it out. But I'm on the open source development team for Mesa, which is agent-based modeling in Python. Right, all volunteers. It started at George Mason, where I did my PhD work, hence the T-shirt. As did Jackie. So real quick, just a quick background. What is agent-based model? Right, so it's a theoretic approach, very much, from the work of Herbert Simon and Sciences of the Artificial, right, where now that we have these computers, we could do science and explore areas that just previously, nonlinear dynamics, they're just previously too hard to do kind of manually with closed form equations. Right, and so it's generative science. It's from a philosophical standpoint, it's a deductive reasoning, right? Instead of analysis, where you break things down, it's synthesis, right? So kind of the catchphrase of complex adaptive systems is where the whole is more than the sum of its parts, right? So you can't break it down. By bringing things together, you create novel behavior that you couldn't by examining each of the pieces and parts, right? So human beings are a great example of that. If I took you apart, I would not be able to put you back together, right? This here, your second order logic is another kind of catchphrase in it, where the idea in this is if I didn't grow the system, if I didn't inside a computer, simulation, grow the system of interest, then I failed to explain it. Now, the real challenge with this is that if I did grow it, right, if I create the statistics on my laptop that I see in the real world, it doesn't mean I actually understand the system, as there could be numerous different types of interactions that produce that same outcome. Right, so just because I grew it doesn't mean I understood it. In this map here over on the right, the Anasazi model from Axtell et al. 2002 was kind of one of the first breakthrough models that showed the limitations of closed form equations and how simulations like this can be useful as they try to replicate the archaeological record of an indigenous group in northern Arizona called the Anasazi. And the kind of poetic way to say the result is that every individual life does matter, because that diversity, that heterogeneity within the population does have an outcome on the overall impact of the system, right, as shown through the modeling and kind of replicating the archaeological record. So what is an agent-based model? All right, it's interactions and emergence, right? So you have a diverse population, heterogeneity, right, that are each acting independently, trying to achieve their local goals or locally optimize their particular situation, and they have these local interactions that produce emergent behaviors. If you work in ecological modeling, they often call these individual-based models, right? So they've done this for fisheries and numerous ecological systems in order to try and understand the dynamics that's keeping that complex system thriving, or to try and come up with interventions to help it thrive if it's suffering, right? So why did you want to use Mesa, right? So we've incorporated lots of lessons learned. The biggest thing, so there's a couple big libraries if you're not familiar with agent-based modeling. And just to, I guess, put in the context of the previous presentation, we talked about multi-agent reinforcement learning, right? They're not mutually exclusive. Just a lot of the work that we do in agent-based modeling is try to create simulations of complex systems as like a virtual sandbox or a virtual laboratory, if you will, to explore our understanding of that system, right, in order to, as a way to kind of test those key dynamics that are producing the emergent behavior that we're seeing, right? So there's a lot of incredible overlap, and actually tomorrow I'm going down to Delft because there's a user community at Delft that uses Mesa. So since I'm here, I figured to go and stop and see some of the professors, right? But with Mesa, so there's a couple big libraries. You have Mason, which is also out of George Mason, Java-based, Repast, which is out of Oregon National Lab in Chicago, and then NetLogo. And NetLogo is probably the easiest to use if you're coming from a non-technical background. But with Python, which is also pretty easy to use, you get the connection to all these other libraries, right? So like like the various deep learning libraries, machine learning libraries, scikit, TensorFlow, PyTorch, OpenAI, et cetera, et cetera. So you're able to connect to all these other libraries, bring in lots of data to help set up your models and things of that nature, right? And we're growing. We are now, as of this past spring, the only, from what I can tell, NUM-focused affiliated agent-based modeling platform, right? And we're trying to expand out as a volunteer organization in order to make it so it's more, it's a sustainable kind of community, just like Python is. So why wouldn't you use Mesa? Well, it isn't fast. If you start getting into really big models, right? So Python, mostly because of the global interpreter lock, you can't do multi-threading and stuff. So if you want a really fast model with billions and billions of agents doing very complex behavior, you got to go to lower level languages like C, C++, Java, etc. All right, I don't know if it's ever going to be done, right? We keep building it. We just reached 1.0 this past summer. But we're getting better, and we're working aggressively to kind of expand the community. All right, but Python, the language is working to improve itself, so it can do things like multi-threading. All right, have extensions into HPCs in the cloud. Actually, Jackie's working on that for a dissertation. Right, and we want to make it more stable, so we have this resilient ecosystem that will sustain beyond the people that are currently involved in it. All right, so if you have a laptop and you'd like to build a model or kind of see how it works, otherwise I'll walk through it. So I'll try and adjust as I can throughout this. All you have to do is go to these things. Got a couple options for you, right? So what we're gonna follow, right, is if you just search, if you just search Mesa read the docs, right, then you'll come up. This should come up right away. All right, and this is our documentation for it. This is our introductory, and then we're just going to follow the introductory tutorial, which is the Boltzmann wealth model. All right, there's a couple other options if you want. So they also have the tutorial in Jupyter Notebook. All right, as well as. So this is a GitHub repository of mine, Edge of Chaos, so Hitchhiker's Guide to the Galaxy, mentioned once before, right? The answer is 42, all right? And then you could go to the Mesa tutorial, all right? And there's a Google Colab, so you got Mesa tutorial here, all right? In just a second, but if you click this Open in Colab link, then you get kind of like a slightly cleaner version that doesn't have all the explanation that you could just follow along with, or, right, since thanks to the marvels of, in this case, Google Colab, what I'll be using is just this, just a Colab instance where we'll be building the model, all right? So it is not one of the standard builds for Colab, right? So you just have to install Mesa, okay? And then it's pretty easy. You're just going to copy and paste here. So if you go down to setting up your model, right? So really, what is agent-based model at a more granular level? Right? Is if you just install this, is you use typically object-oriented programming, makes it easier, very easy to understand. Oops, excuse me. All right, and then you build a class of a money agent. So first off, what's the Boltzmann wealth model? Right? So where I, as an agent, am just going to see other agents and give them money, right? So I got X number of some unit of money, right? And I'm going to give them that money and then go to the next person, and they'll the next agent will give me money, et cetera, and we'll kind of see how this plays out, right? And I think, very similar to the aggregator we saw in the earlier presentation, you have a, n number of agents, right? But then you have a manager, which creates lots of interesting dynamics, all right, that's integrating these agents and kind of monitoring them and deciding who goes first. Sorry about that. Right? And so that's really, at its basic, that's really all we're doing, right? It's just using the power of object-oriented programming to cause these interactions, and after that, it is really the sky is the limit, right? Whether you want to use deterministic functions and how these agents behave, or you want to use, kind of more randomized behavior, reinforcement learning, et cetera, to integrate it. And what Mesa provides is just, like all things in kind of open source libraries, you're just trying to reduce the amount of cost that it takes you in order to build one of these models, right? And towards the end, I'll show you how we're trying to build out the ecosystem. So the vision, if you will, right, is that to make these types of simulations as easy to use as you'd use any kind of like machine learning thing like a scikit-learn or a TensorFlow, right? So as a for instance, right, since there's a lot of COVID modeling going on right now, if I was like, say, an elementary school principal, right, I could rapidly build a simulation, right, of my particular elementary school with the right geography, behaviors of a kindergartner versus a 6-year-old, et cetera. All right, and I don't need to know all that, be able to know how to code all that out. I can reach out to the rich ecosystem that is the open source community, bring in all those pieces and parts, and then sit there in my local area and kind of play around with what, based off the resources that I would have, based off the policies and resources that I have, whether it's masks, antibacterial soap, et cetera, right, in order to try and come up with, well, what's the best intervention for this current pandemic to try and still educate my students while mitigating the spread of COVID, right, and also make a more informed decision, right, on whether or not they should, go to virtual learning if you have that option, or keep everybody in school. So I think, very much in line with the previous talk is, what does this ecosystem look like so more people can leverage these computational tools in order to make better decisions, right? From the day-to-day, keeping elementary school running, transportation infrastructure, up to kind of international relations and economics. All right, so now part 2 of that is all we're going to do. So this is really the base, right? It's just, in this case, we're only going to really have 2 class objects. So a money agent and a money model, and then we just expand off of that and start adding behavior. All right, so just because it's faster, I'm just going to copy this section here. All right, so now that we've uploaded this, all that we have now is one behavior. So if you're not familiar with agent-based modeling, you have what's called step functions, right? Where this is, and it's just cultural, that's what they call it, right? Where the manager, right? So you have a scheduler. In this case, we use random activation, right? And you've, I don't know why that keeps coming back up. All right, and these like little details become really important, right? Because they found, actually, our colleagues at Mesa found that it's that the order of agents actually does matter, right? So this becomes a great problem, kind of going back to physics-informed neural networks in these large complex systems where you have a massive search space of what can actually happen, right? As things as seemingly mundane as if you have the same agent going first every time, it all has an impact on your results, right? And so in this case, a typical way to deal with that is like, well, we'll just randomize it, right? Or pseudo-randomize it, right? And so you randomize it. There's other ways, and Mesa provides other functions like staged activation, where every agent will go through, kind of make their decision, and then they all go at once, right? But all these little details, much the butterfly effect, right? The Lorenz attractor, do have an impact on it. So, excuse me. All right, so you have, so we provide the scheduler, so you don't have to code that out. Load up each of these agent objects, right, into your scheduler, and then and then you just kind of run steps through that, right? In this case, just to start out with, these agents are just going to say, hi, right, I'm so-and-so. right? And then you just instantiate that model object, all right, and run it, run it for one step, right? And so each agent just has a very simple behavior where they say, hey, and who they are, right? Well, that's not very interesting, nor does it provide anything overly insightful. So now I'll replace the money agent object, right, where we're going to start giving them behaviors to see what kind of results can occur. This actually works. Okay. All right. So in this case now, right, Boltzmann wealth model, very simple model. All right, where you say, I'm going to look at the other agent. So if I have essentially a list of 10 agents, I'm going to randomly select another agent and give them one bit of wealth and detract my wealth, right? And then we're going to run that for 10 steps. I forgot to do a print statement. All right, so we've run that model. All right, now we want to see the results. All right, and as you can see, right, not very exciting, but right, some agents have nothing. Many. So of the 10 agents, right, 3 have nothing, 4 have 1 unit of money, right, and then 3 have 2 units of money, right? And then we just do it a lot, right? So very similar to the earlier talk today. Oops. All right, we could run it 20,000 times, and interestingly, this is not, the ability of computation is not necessarily well respected or understood in a lot of the social science magazines, where they'll ask you for like, oh, we need your p-values for this. Be like, well, I can just run my simulation more and ensure I get a significant p-value. All right, so it is interesting to do a lot of computational social science, so you kind of get this clash of cultures. All right, but as you can see here, so now we've run so you got one model, right? We've run it 100 times, right? And then each model has a step, right? And then we just want to get a histogram or we run each one of those models 10 times, and then we want to get a histogram of all the agents that are in there, or a histogram of the wealth of all the agents when you see at the end, right? And you see with just this random model, which is why I guess we used it, you start to get some maybe novel results, right? We might expect, hey, if you just have agents randomly transitioning money, right, what's going to happen is they're all still going to end up with 1 at the end, more or less, right? But instead, you start to get this, just where one agent actually has, is way richer than most of the agents, right, that don't have anything, right, just through these random interactions. All right, and then Mesa also has the ability that you can add space to it, right? So again, it's all, how do we provide a rich ecosystem? Let's see where this one goes. How do we provide a rich ecosystem for researchers, scientists, and practitioners so they can rapidly build simulations about their area of interest to make more informed decisions, right? To kind of create that collaboration between the human and computational tools so we can make better, more informed decisions, right? So in this case, I'll explain it just once I copy it in. Actually, let me just do all this. All right. So again, if you go to the tutorial, all these things are there, and you can copy and paste or kind of get into the details as much as you see fit. One second. Okay, so what have we done, right? So again, you have so typical parts of agent-based models. You have some kind of schedule that has some kind of time-activated sequence because computers are sequential, particularly Python, right? And so it goes just step by step. Right. Next up, in this case, we have the multi-grid, right? And what that means in Mesa, right, is the fact that you can have more than one agent in that grid. right? So you can, particularly if you're using like ecological models like wolf, sheep, predation, or something like that, you can have a grass agent and then a wolf or sheep agent also on that particular spot, right? And the good thing about Mesa is all this stuff is kind of easily understood, right? All the code is easily available inside a GitHub repo, right? So if you actually want to see, okay, what's inside the multi-grid, right, you could go in there, right? And you could go in there and identify how it's actually functioning. It's just a dictionary where the key, right, is a cell location, right, and then a list of agent objects that would be in there, right? So you add a grid, right? We throw them. So lots of randomness in here, but we throw each of those agents somewhere onto that grid, right? And then we place them on there, right? Then for the agent, we got to add some more complex behaviors, right? And again, these are all pretty simplistic for the sake of the tutorial, right? But really, the sky's the limit, right? Whether you want that to be some kind of trained machine learning processor, right? Whether you want it to be some kind of deterministic algorithm based off your particular field of study, right? And so in this, what Mesa provides is a bunch of functions again to make it easier, so we could build simulations more rapidly, right? So you could get the neighborhood, which is how do I see the 8 neighbors around me, or you could do 4 neighbors if you are so inclined. In order to so how do I get that neighborhood, all right, and then select an agent. So now instead of being on a one-dimensional line, think of a list, I'm now in 2-dimensional space and can look at all my neighbors and say, who do I feel generous enough to give this money to, right? And then if you have some money left, right, then you hand that money off.
Yeah, I have a very naive question.
Yes.
So pardon me for,
No, please.
but it seems like that non-determinism is a result of your pseudo-random number generator.
Well, yeah. So it depends on the model that you build. You can absolutely make these very deterministic if you want. All right. But a lot of times, because you're dealing with stochastic systems, that's how you're doing it. In this case, it's a very simple model.
Right. So
Yeah.
you are trying to infer some statistical characteristics of this simulation. So my concern is, aren't you just articulating the statistics of the pseudo-random generator rather than real physics, if you will?
No, so that's how you kind of confirm or deny your simulation. So the Boltzmann wealth model was confirmed through other mechanisms, right? Through kind of standard closed form equations, economics, and things of that nature, right? And then by doing it through this, through these kind of bottom-up simulations, you're able to get those similar results, right?
Do you have the opportunity to have like a real, truly random generator?
Yeah, I mean, I don't think. My understanding is, no, and I'm not a computer scientist by training, but my understanding is there's really no truly random number operators, right? And this is, yeah. Yeah. Oh yeah, I mean, that's so you can bring in any aspect of it that you want, right? And kind of to elaborate on your question, if you look at like the wolf sheep predation, right, which is just a very simple model of wolves eating sheep. They eat too many sheep, they die off, so more sheep produce, et cetera, et cetera. You can look at like the logistics maps of those curves, right, and they're very smooth, right? You can then generate an agent-based model of that, right? And it's not, you get a lot more, for lack of a better description, noise, but it's also technically kind of more accurate noise, right? Because those are the dynamics that are actually occurring, right? And we know from deterministic non-periodic flow, right? Edward Lorenz, that noise actually has a large, can have an impact on the overall behavior of the system over time. Right, so that's where these can really become beneficial, where things that you have to kind of simplify away, we can now use computers to say, well, will this actually have an impact on the overall behavior of the system? Right. That's it. Yeah.
So in this example, the agents are accessing each other's state and modifying each other's state.
Yep.
Are they always seeing the state of the other agents in the previous step, or are there intrinsic race conditions here in the order in which these updates occur?
Yeah. So in this case, right, since we're doing random activation, they will see every agent will go once, and then that in essence updates updates their state, and then everybody sees it from that perspective, right? Now this is where you can select different activation regimes, like staged activation, where the agent would say, okay, this is the situation right now, right? They all go through their decision based off that particular situation, right? And then they all update their state at once, so to speak, because they're making that informed decision. Now, can you get race conditions from that, or like collisions of behavior? Absolutely. And the trick then becomes what hands of the user, so to speak. What are you trying to do with your simulation, right? How are you going to deal with those collisions, right? And an easy kind of agent-based model would be you have two people at a stop sign, or two agents at a stop sign. They both decide to go at the right time or at the same time, and there's a collision, right? And so in this case. And this is one of the critiques of agent-based modeling, right, is that you can kind of bake in any behavior that you want into it, right? And because you could say, wow, this is how we're going to deal with that, because you could say, well, this is how we're going to deal with that collision, right? And then just like all good science, how'd you add that rigor into your simulation, right? How'd you deal with that you're not pre-baking in behaviors just to see what you expect to see, right? And that becomes very much the kind of some art and the science where they combine. Does that make sense?
I'm still not sure I quite understand. Maybe it's because you're working within Python that's sort of fundamentally sequential,
Yep.
and there's no multi-threading here, there's no multi-core execution, and so this is just a sequential execution model, and the order in which you invoke these things is what determines the behavior. That seems a little bit at odds with the principles of agent-based modeling, which are usually about huge amounts of concurrency.
Yeah. Well, no, and that's so we'll kind of do the technical, and we'll do what the simulation does, right? So yes, because of the way Python works, with the GIL, with the lack of multi-threading and stuff like that, right, is that it will always be executing sequentially. Now you could kind of cheat that with like a staged activation, right, where every agent will make their decision, right, based off how they perceive the state, their particular, a state at one period of time, and they'll make a decision, right? And then from that, you could have like, so going back to the stop sign model, right, if they're both at a stop sign, right, and they both decide to go, then you as the kind of model designer have to, well, how do I deal with this quite literal in the collision in my simulation? So yes, it's happening sequentially, but how you specifically code out your simulation, right, is kind of how you deal with the fact that Python, that in real life people are making decisions concurrently, right, and can absolutely have collisions. Okay, any other questions, clarifications? Okay.
Otherwise, the people online have no clue what's been said.
Yeah, I'm just a little confused about whether this is just an artifact of the modeling, or is it the artifact of the system that physics of the system that is underlying your model? So
on why you get this, it's not really a heavy tail distribution.
So for example, when you talk about the stop sign, I mean, there are conscious, like coding decisions you can make, and it seems like the behavior is predicated upon the decisions you make in how you code the proceeding from the stop sign function, right?
Mm-hmm.
So what is that really trying to prove? I mean, you're just showing that this is the outcome of that function being used in that situation, right?
Yeah. Well,
Does it say anything more than that?
Yeah. Well, yeah, and that's where you get emergent behaviors, right? So if you have a bunch of local interactions, where you say, hey, this is how people will behave in this kind of situation, so to speak. Right, then you start to get novel emergence, or you can get novel emergence that you didn't expect to happen, right?
But
Based off
still
those
a sequential program, right?
Yeah.
So I posit that if you have a truly random, variable that you can read, then you will be able to mimic true concurrency. I hope Professor Lee agrees with that.
Thumbs up, thumbs down.
No.
Thumbs
Thumbs
down.
down. Okay.
Something to discuss over lunch between you two.
Okay. Then clarification questions? Okay. So, well, I guess talk pseudo concurrency later. But so now, it's another feature, right? You can add to the grid so that agents can now move in two-dimensional space, right? In order to kind of add some more features to the simulation, right? Again, this is just very much a toy model for demonstration purposes. Make sure. Oh, and then I forgot to copy something over. Oh, I forgot to run it. Yeah, well, that's all right. Let's go over here. All right, so I'm gonna switch over, right? Live coding, always somewhat hairy. All right, so we have, so each agent gets placed onto a point of the grid. For the love of, give me 1 second just to fix this real quick. Money model. Okay. There we're now back on track. All right. So we've added them to the grid. All right. Actually, I don't think I put it on there. So now they're switching. They're moving from place to place on this grid. If you run this particular and so already, like with the simple kind of behaviors, you start to get some pretty lots of activity occurring. Right, now the next thing you want to do then is add what's called a data collector. Right, so now these agents acting autonomously, if you will, making decisions about how to spread money, or giving money to somebody randomly, receiving money from somebody else, if they're in that same position. All right, so use something called the Gini coefficient, which is just if with economics, this is just a measurement of wealth, where 0 means if everybody has 1 unit of money, right, then it's perfectly distributed, so that's 0. If one person or one agent in this case has all the money, right, then you have then your distribution is 1, right? And you can see you kind of randomly spread this money, right? The Gini coefficient here goes up pretty high. But the significance of it, right, this is kind of talking Mesa, right, is that you have a data collector, right, and orders as the model's proceeding, right, that you're starting to collect all that money. Or you're starting to collect specific data that you're interested in based off the statistics that you want to see out in the real world, right? So as for instance, a couple years ago, George Mason, Princeton, Oxford ran a housing model of the greater DC area, so roughly 2 million houses, right? And they said, well, we want to see, if what policies may have impacted the housing bubble that occurred in 2008. Right, and so the way they did this is, every agent made decisions about whether or not to buy or sell, and whether or not they could, based off the banking regulations, right? Is that a collect out, what they use is something called pattern-oriented modeling, right? We say, hey, we have these 9 statistics, right, of the larger DC metro area housing, of the larger DC area kind of housing market, right? Can we build a simulation that matches up against those, right? And so to the point where you're trying to, how'd you mess with these, or how'd you understand these complex systems where it's like, what were each individual is making a decision, right? The Federal Reserve Bank, was making policy decisions on whether or not to raise or lower the interest rate, right? Can we recreate what happened? And so the first step was that they, built out the simulation based off a lot of real-world data, which is always always one of the hardest parts. They brought in that money, or they used that data, fed it into the agent-based simulation, right? Had the agents make decisions, and of the 9-ish statistics that they were looking at, they successfully recreated 8 of the 9. right? And so from that, you can then start to take kind of policy intervention decisions to say, well, we think we got a pretty good understanding of why we saw the housing bubble and what it did, right? And this is where, particularly social systems, other complex adaptive systems, this becomes the kind of, right now, currently accepted methodology to try and understand them, right, and develop interventions, right? Where it'd say, okay, this is a system we have, can we recreate it, right? And then the flip side of that is once you get it, right, can you create interventions or conduct actions that will influence the behavior of that system, right? And so this is where you start to get some additional benefits from the traditional machine learning, right? Where, when COVID happened, right, a lot of Google, Amazon, et cetera's machine learning models started to break, right, because they were seeing behaviors that they had never seen before, right, because of, because of the pandemic. Right now, the benefits with simulations like this, right, is that once you kind of say, okay, we think we got a pretty good idea of those dynamics that are producing this behavior, right, it becomes that goal is it becomes a policy or action tool, right, that you can use in order to make better decisions, right, and shape the behavior of the system, right, based off those tools, right. But the caution I always give, to quote kind of the statistician named George Box, right, is all models are wrong, right, some are useful. And I think to the earlier discussion today, right, the real benefit of this doesn't become necessarily the output of that model, right, where somebody's sitting there going, oh, okay, let me build this model for you and tell you what policy decisions to make, right? It's that challenge of sitting there trying to identify what dynamics are influencing the behavior of the system, where you can, because you're the one kind of building and putting all that stuff together, or your team, right, and saying, and learning from that experience on trying to recreate the emergent behavior of that system, right? So every agent-based model I've known that's worked very large problems for the U.S. government, down to local policy dynamics of parks in Delaware and stuff like that, to COVID modeling, right? The real benefit they typically get from their simulations is the process of building it, right? Of having to think through what are those interactions that are causing this emergent behavior to occur, right? And so the features, if you will, that Mesa provides then is just the managers, grid, random activation. So you got your space, random activation, and agent behaviors. All right, so you don't have to build those all from scratch, right? Then you can, if you have statistics that you want to match, right, like this Gini plot. So I think to one of the earlier questions, right, this reproduces behavior that's been known, as seen out in the real world, and is understood by economists as well-known behavior, right? But then based off what you're collecting, you can collect all this information, or you can collect information at every step on the way, so you can kind of explore the behavior of this virtual laboratory more extensively, right? So in this case, you could kind of think of this one. We're looking at how much at a particular step, how much wealth an agent has, right? Or track the individual kind of wealth of each agent, right? So you might think like, oh, if you were rich at one point, you were always staying rich, all right? But through these types of explorations, you can also find somewhat maybe counterintuitive results. Where in this case, this person was this particular agent was going through a lot of peaks and lows, and how much wealth they had at a given time, right? As the agents were just randomly exchanging wealth, right? And then from that, you can start to say, well, hey, this is not matching what reality is. Maybe I should, maybe there's a fundamental flaw in how I'm understanding this system, right? That's what this does is just saves it, so you can save this money out, right? Now this is, if you want to see what it looks like on the grid, all right, this is just an example, just a heat map of the different amount of money on each grid, right? And since you can have multiple agents in one spot, this could be 3 agents with 1 unit each, or it could be 1 agent with 3 units. Now, to the problems, right, with these types of systems, right, is that they're highly parameterized, and they can have a lot of different options, right? So you have to do what we call parameter sweeps, right, to see as much of the search space as you can. All right, and so we have another function called batch run, right? Which then takes it, and so now you got 10 agents to 500 agents on a 10 by 10 grid, but you could also do from a I guess a 5 by 5 to 1,000 by 1,000, right? And then explore that whole search space, right? Although Python at this time doesn't do multi-threading, they do multi-core operations, right? So if you have a lot of processors, it's embarrassingly parallel, and you can split them off across a lot of those, across every core that you have, all right? And you could kind of get around the guild to an extent that way, all right? And then, like anything, when you really get these large models, all right, then the challenge becomes how do you analyze the data that you have in there? All right, so it's still running, so running off one core. Kind of get limited on that. All right, and then you can explore your results to understand, what are those possible results of the search space that are out there, right? And so the other bits that we're not going to show you today, just in the sake of time, right, is that they have we have visualizations, right? So open up a browser-based app. If you just open up a server, right? So you can see it occurring dynamically, right? As well, and then you can just do different stuff with that. And that's currently in JavaScript, all right? So let me go here real quick. So now the question becomes, right? As this is still running. Right, the trick then becomes how do we make it more easily available? So if we look at coding as the next revolution, from the printing press and stored knowledge, right? How can the long-term, long-range challenge we're working on, as I could tell, is probably like orders of magnitude harder than standard machine learning libraries as you deal with these dynamic systems. Is there a way to build out an ecosystem, right, to make it so you can rapidly build these simulations to aid human decision making, right? And so one project that I'm working, which I'll go to in just a second, is called Mesa Data. All right, and then there's also Mesa Behaviors, right, where these try and, to that point of how'd you get to a valid model, right? Right, and these all have Binder, which just spits up a Google instance for you. All right, of data pipelines is, say I'm looking at country X, and I want to understand why that the behaviors of that population, so to speak, and I need a valid model. This one will use the worldpop.org data set, right, and download essentially a population of that and kind of smooth that population because in this case, right, there's always some kind of data cleaning. You'll get a population where it has like 6.5 people in a 11 meter square area, right? There's no such thing as 0.5 of a people. You're either alive or you're not, right? And so this smooths that out in order that you can have a valid synthetic population, right? Because it matters. If you take the country of Niger, for example, that has a massive youth bulge that's about to hit, right? That has impacts on how that country will behave if you have a more normally distributed, population, age population, right? That will fundamentally change the behavior of that population. We also currently have, and these are all very very nascent, if you will, right? As we try and deal with this problem, like crop yields. Right, so using famine land data assimilation set, right? How'd you pull in that data, right, to have your starter population or to have your starter potential crop yield, and then deal with different types of, rain and things like that, and simulate forward in time to anticipate, what's going to happen if this country that's already kind of starving. What might happen, and what are some ways that we could deal with it to prevent some kind of massive humanitarian disaster. All right, to that end, we also are doing, what's the easiest way to get here? Collecting a library of behaviors. A second, let me go back here. All right, and this one's called, all right, where you have, so SIR, if you're not familiar with SIR models, right, susceptible, infected, recovered, right? That's pretty critical for pandemic modeling, all right? Or the bilateral Shapley value for coalition game theory, right? How you form groups and break up groups, all right? But all this kind of leads to the larger idea of, very much in line with a lot of the talks we had here, is how do we integrate tools, all right, to make better decisions? Right. In this case, is how do we integrate the tool of simulations to make better decisions, or understand the complex dynamics of, in my case, how your society is occurring, or how an ecological system's occurring, right? And so the thought is, well, can we build out this rich ecosystem where critical knowledge is stored in code, right? And then take that knowledge and integrate it together in these complex, in these simulations, so we can understand the world a bit better, right? So, for instance, on the crop yield, I'm using a library called the Python crop simulator, all right, out of England, right, in order to simulate the growth of crops for that particular data pipeline. All right, and so the larger kind of vision in all this, particularly the Python ecosystem, which is pretty rich, has a somewhat a lower obstacle to bear, a lower barrier to entry than a lot of other computing languages, right? Can we leverage that ecosystem to allow people to build these simulations more effectively? And then as we kind of fast forward in time, what does that ecosystem look like, right? So again, go back to the elementary school principle. They could take that expert knowledge from across the world, throw it together, right? And now make better decisions that when you multiply that across, tens of thousands, hundreds of thousands elementary schools, right? We now are able to deal with things like pandemics more effectively and efficiently. Right, because we're kind of putting that power into the hands of the people, if you will. So, I think that's, again, if you want to play with any of these things. One second. All right. Oh yeah, so one final bit. This is an open source project. So if you want to get involved, all you have to do is go to our GitHub page, all right, join the discussions. We have a link on Element, all right, or Matrix, if you will, just it's like Slack or something like that. And I mean, it's all voluntary, all just a bunch of agent-based modelers trying to understand the world better. And because it's such a boutique field, you don't even have to be an agent-based modeler to join. All right, we use all the help we could get. So with that, are there any questions?